In the previous lecture, we discussed harmonics and standing waves. Now we're going to actually apply those concepts to instruments, to musical instruments. Now, many types of examples of musical instruments exist that use strings to produce the sound. Some examples include the piano, the guitar, and the violin. Now, when the string on that instrument is plucked, it begins to oscillate. It begins to vibrate, and that vibration creates a standing wave on that string. Recall that a standing wave is essentially a wave that contains nodes and antinodes. Nodes are simply regions where destructive interference takes place, and antinodes are regions where constructive interference takes place. So in this example, for example, these two regions are the nodes, and this region is the antinode. Now, standing waves are only produced at specific frequencies known as resonant frequencies or natural frequencies, and each string has its own natural frequency. Now, the lowest possible frequency that produces a standing wave is known as the fundamental frequency, which is also known as the first harmonic. The n value of such a wave is equal to 1. And one example is shown in the following diagram. So let's suppose this is a string found on, let's say, a guitar. So notice that the first harmonic has two nodes, one antinode. And the length of our string is given by the distance from this point to this point. So that means the wavelength of our oscillating, our vibrating wave is 2 times the length of that string. Now, the next harmonic, known as the second harmonic, has an n value of 2. And it looks something like this. Notice now we have 1, 2, 3 nodes and 1, 2 antinodes. And the length of our string is still this distance, but the wavelength is now reduced by a factor of 2. So the wavelength is equal to the length of the string. And we know that by using the following formula. So if we have a string that is fixed at 2 points, as shown by these two diagrams, the equation that relates the harmonic number, the wavelength, and our distance, our L, length of our string, is given by this formula. Our length of the string is equal to the product of the harmonic n, the wavelength at that harmonic, lambda n, divided by 2. Now, recall that the velocity is equal to the product of our frequency at that harmonic and the wavelength at that harmonic. And if we combine these two equations, we get the following result. So we essentially take this equation, rearrange, and solve for lambda n, and plug that into our lambda n in this equation. And we solve for Fn, our frequency at the nth harmonic. And we get the following result. The frequency of our vibrating string at the nth harmonic is equal to the product of n and v, where n is the harmonic number, v is the velocity of our wave in that string, divided by 2 times the length of that string. Now, recall that the velocity of a mechanical wave only depends on the type of medium that we're using. And the equation is given by taking the square of the ratio of the tension Ft in the string to the mu, where mu is the mass per length of our string. So the velocity only depends on the type of medium, on the type of string that we are using. For example, the velocity on a heavier string as compared to a lighter string with uniform tension is lower, and this means that the frequency on that string must also be lower. So let's look at the following example in which we're going to use these formulas to calculate a certain quantity. On a certain stringed instrument, the highest note corresponds to 160 times that of the lowest note. If the length of the string producing the highest note is 10 centimeters long, find the length of the string producing the lowest note. Let's assume that the tension and the mass per unit length of the two strings is exactly the same, and let's suppose we're dealing with n equals 1, so the first harmonic. So basically what this problem tells us is the velocity of our wave produced in both of the strings is exactly the same because the tension and the mass per unit length is the same in both strings. So let's suppose V1 is the velocity in string 1 and string 1 corresponds to the highest note. The velocity in string 2, V2, is given by this variable, and this is the velocity in the string that corresponds to the lowest note. Now, from this equation, from equation number 2, V1 is equal to lambda 1 times F1. And V2 is equal to lambda 2 multiplied by F2. Now, because the velocity in string 1 and string 2 are the same, V1 is equal to V2. So that means the product lambda 1 times F1 is equal to the product lambda 2 times F2. So let's rearrange our equation, and we get the frequency on string 1 that produces the higher note divided by our F2 is equal to lambda 2 divided by lambda 1. So we are told that the string instrument has a highest note that has a frequency that's 160 times greater than the frequency on the lower note. So that means F1 divided by F2 is 160 divided by 1, or simply 160. And this is equal to lambda 2 divided by lambda 1. Now we know lambda 2 or lambda 1 corresponds to a length of 10 centimeters. Now we can use this equation and solve for lambda 2. And we find that the wavelength of our string, the second string that produces the lowest note, is equal to 160 multiplied by 10 centimeters, or 1,600 centimeters is the wavelength of that string. Now we want to find what the length of that string is. To find the length, we have to use equation number 1. Our length is equal to n times lambda n divided by 2. Now we are told that n is equal to 1. So that means n is equal to 1. And so we have the length is equal to 1,600 centimeters divided by 2. So we get a length of 800 centimeters, or equivalently 8 meters. So that means the length of our string that produces the lowest possible note on that instrument is 8 meters long.